The separation of propane-propane mixtures is important in the process industries, and for propene feedstocks to the polymerization reactor, the purity requirements are about 99.95% that is currently achieved in distillation operations. There's considerable effort in the development of metal organic frameworks and ZIFs for separations of propene-propane mixtures. Many of these adsorbents are selective to propene, and therefore the desired product is only recoverable in the final countercurrent vacuum blowdown step. In order to achieve high purities of the desired propene product, it is important to have adsorbents that practically exclude propane from the pores, because any propane left in this final blowdown stage will contribute to low purity of and recovery of the desired propene product. One of the schemes that is used in practice is to exclude propane from entering the pores by relying on kinetically driven separations. For background to the theory and practice of kinetic separations, I invite you to examine my paper in Chemical and Bioengineering 2024 that is available online. The candidate adsorbents that are suitable for kinetic separations are Chabazite, Cast 7, that practically exclude propane from the pores, allowing high purity propene products to be recovered in the final vacuum blowdown step. In today's presentation, I'm going to talk about separation of propane mixtures using ZIF8. This shows the crystal structure of ZIF8. Per unit cell, there are 2 cages. The volume of 1 cage is 1,168 cubic angstrom. The cages are separated from adjacent cases by windows that are 3.3 angstrom in size. This is the crystallographic size of the window aperture. The size of a single ZIF8 cage is larger than the single cage of a DDR zeolite or even faucesite. There are subtle differences in the bond lengths and bond angles between propene and propane, and the result is that the intercage hopping of propene occurs about a factor 100 times faster than that of propane. The windows of ZIF8 are flexible, and to demonstrate this, I show animations created from MD simulations where we look along this axis Let's have a look at the animation. You see, the windows are flexible and they open and shut like saloon doors in a Quentin Tarantino movie. In a paper that is just online in ACS Nano, experimental results are presented for breakthroughs of 50-50 mixtures of propene and propane at a temperature of 298 Kelvin in a packed tube with different crystal diameters of ZIF. The diameter is 2 times the radius of the crystal. The experimental data are shown by the dashed lines in these 4 cases. The red line indicates the breakthrough of propene, and the blue dashed line indicates the experimental data for breakthrough of the saturated propane. For a particle diameter of 9 micrometers, particle diameter of 72 micrometers, 141 micrometers, and 224 micrometers. For very, very small crystal diameters, say in this case of 9 micrometers, the propene exits the fixed bed slightly earlier than propane, because the adsorption strength is ever so slightly in favor of the saturated propene. Indeed, the adsorption selectivity of propane to propene is of the order of 1.1 for propane-propane mixtures. The continuous red and blue lines are simulations of transient breakthroughs using the model I have described in my 2024 paper and cited here. This model uses the Maxwell-Stefan diffusion formulation, taking due account of thermodynamic coupling. Also demonstrate in my paper that the LDF model is just not good enough to describe breakthroughs for kinetic separations. In all 4 cases, the transient breakthrough simulations are in fair agreement with the experimental data that is shown by the dashed lines. And they show that with increasing particle diameter, the breakthrough of saturated propane occurs earlier. And that is important in PSA separation schemes, because the achievement of high purity of propene that is recovered in the vacuum blowdown step is the purity is higher if propane is practically excluded from the pores. Therefore, increasing particle diameter is desirable. Let's look at the transient breakthroughs for a fixed bed packed with ZIF8 with a particle size of 9 micrometers. These experiments described in the ACS Nano paper that is just available online were conducted for 50-50 mixtures at 298 Kelvin with partial pressures of 50 kilopascal each for propene and propane. The flow rate of the gas mixture at the inlet is 0.4 milliliters per minute. From the dimensions of the fixed bed and the mass of adsorbent used, and the specified length of the packed bed and the crystal framework density of ZIF, which happens to be 924 kilograms per cubic meter, we can determine the bed voidage, and if the volumetric flow rate at the inlet Q0 is taken to be 0.4 milliliters per minute, as in the experiments, we can determine the interstitial gas velocities. These bed voidages, interstitial gas velocities, and bed lengths are important in breakthrough simulations. Let's have a look at the simulation animations. Remember, red is propene and blue is the saturated propane. This, let's see how the profiles develop. In the gas phase, along the length of the fixed bed. For a chosen particle size of 9 micrometers, as is the case here, we see that the two components, propene and propane, traverse the bed practically at the same time, and this is because for the chosen particle size of 9 micrometers, intracrystalline diffusion limitations are of negligible importance because of the small particle diameter. This is because the gas molecules do not have to traverse very far to reach the center of the crystal and achieve equilibrium. And both components, propene and propane, exit at practically the same time, as shown by these continuous red and blue lines. So a choice of 9 micrometer particles will not lead to exclusion of propane as is desired. We need to increase the particle size. Let's look at the experiments with a particle diameter of 72 micrometers. Since the particle size is larger, diffusional influences are stronger. And if we look at the transient breakthrough simulations, we see that the saturated propane is practically excluded from the pores and traverses along the fixed bed in the gas phase faster than the unsaturated propene. Recall that the blue line is the breakthrough for the saturated propane, and the red line is for the unsaturated propene. For for 72 micrometer particle, diffusional influences are stronger than for 9 micrometer particle, and the saturated propane is rejected into the gas phase and leaves the bed earlier than propene, as shown by the continuous blue line and red line in this breakthrough curve. We now examine the breakthrough simulations for a bed packed with ZIF crystals of 141 micrometers. The red line and the blue line are the breakthroughs of propene and propane. The continuous lines are the simulations, and the dashed lines are in the experiments reported in the ACS Nano paper. Let's look at the animations of the simulations. What we are looking at is the development of the concentrations of propane, the blue line, and propene, red line, in the gas phase as they traverse the fixed bed. The y-axis shows the concentrations in units of moles per cubic meter. Diffusional resistances are stronger than in the previous example, where we had a particle size of 72 micrometers, and therefore the distance of separation between the blue and red lines is larger, and the saturated propane is excluded to a greater extent from the pores of ZIF8. We now examine the animations of the breakthrough simulations for a bed packed with ZIF8 crystals with a diameter of 224 micrometers. The diffusional resistances are significantly higher, and the breakthrough of propane, which is shown by the blue line here, occurs significantly earlier than the breakthrough of the unsaturated propene. That is shown by the red line. The distance of separation between the breakthrough of propane and propene is important in order to achieve propene of high product purity in the PSA scheme for propane-propane separations. Having established the accuracy of the Maxwell-Stefan diffusion formulation for modeling of kinetic separations of propene-propane mixtures using ZIF8, we can proceed to examine carefully if there is an optimum crystal size that would yield the best separation in the adsorption cycle. To do this, we conducted a series of simulations with different crystal sizes, including the 4 sets I discussed earlier, and a few more with increasing crystal diameters. The productivity of purified propane in the adsorption cycle with a purity of 99% plus is determined from the simulation data. We see that the increase in the crystal diameter increases the productivity due to the increasing diffusional influences till a particle size of 224 micrometers is reached. Increasing the crystal diameter beyond that point reduces the productivity, because with increasing diffusional resistances, say in excess of with using particle sizes in excess of 300 micrometers, both propene and propane are tend to break through earlier, and the productivity of purified propane is reduced. So the important message is there is an optimum crystal diameter. The same set of data here is plotted using the diffusional time constant as x-axis, where d sub 1 is the Maxwell-Stefan diffusivity of propene, which is 1 times 10 minus 11 using the simulation data. R sub c is the radius of the crystallite, ZIF. The concept of optimum crystal diameter is discussed in detail in my paper in 2024 in chemical and bioengineering that is available online. A second campaign of experiments with varying inlet flow rates were conducted and reported in this paper in ACS Nano 2024. In all these three cases, the particle diameter of ZIF8 in the packed tube is held constant at 9 micrometers, and the flow rates are varied from 0.1 milliliters per minute, 0.2 milliliters per minute, and 0.4 milliliters per minute. The dashed lines are the experimental data, and the continuous lines are the breakthrough simulations using the Maxwell-Stefan diffusion formulation, including thermodynamic coupling. The Maxwell-Stefan diffusion and formulation and the modeling of the breakthroughs in fixed beds is described in my paper 2024. There is good agreement between the simulations and experiments, but we note that for all these three flow rates, the breakthroughs of propene and propane occur practically at the same time, indicating that the diffusional influences are not strong enough. In order to understand that, let's see what the influence of varying inlet flow rate is. We can determine the interstitial gas velocity, V, which is the superficial gas velocity divided by the bed voidage. And this is related to Q naught, the inlet flow rate, the diameter of the tube, the mass of adsorbent, the crystal diameter, and this is the length of the packed bed. The contact time between the gas mixture and the crystals, the average contact time is the length of the packed tube divided by the interstitial gas velocity. In all these three cases, the contact time is large because of the low gas velocities and low volumetric flow rates used in these experiments. In order to increase the diffusional resistance, we need to employ higher gas flow rates, i.e. shorter contact times. Here are set up 3 experiments at higher flow rates of 1.7 milliliters per minute, 3.8 milliliters per minute, and 7.9 milliliters per minute. The tube is packed with ZIF 8 crystals of 9 micrometer diameter. The experimental data shown by the dashed lines are from this ACS nano paper cited here. The continuous solid lines are the simulations using the Maxwell-Stefan diffusion formulations as described in detail in my paper in Chemical and Bioengineering 2024. In all 3 cases, there is good agreement between the breakthrough simulations and experiments, and we see that with increasing flow rates, i.e. reduced contact time, the breakthrough of propene occurs later than the breakthrough of propane, and this is desirable for kinetic separations of propene-propane mixtures. For the optimum crystal diameter of 224 micrometers, we conducted a series of simulations in which the volumetric flow rate is varied, and as a result, the contact time between the gas mixture and the crystal, which is the length of the packed bed divided by the interstitial gas velocity, is varied from say 5 seconds to about 50 seconds. If the contact time is very large, then diffusional influences are low because there is enough time to approach equilibrium. So diffusional influences are stronger if the contact time is reduced till an optimum contact time is achieved. Reducing the contact time further reduces the productivity of purified propane in the adsorption cycle. The concept of the optimum contact time is described further in my 2024 paper that is cited here. We've established the optimum diffusional time constant and the optimum contact time for increasing the productivity of purified propane in the adsorption cycle. The product of the diffusional time constant in units of seconds to the -1 and the contact time in the units of second, that is optimum, is 0.04. Now this product can be achieved in many ways, this optimum product of diffusion time constant and contact time. It can be achieved by choosing a inlet volumetric flow rate of 14.9 milliliters per minute with a particle size of 40 microns, or with an inlet flow rate of 4.61 milliliters per minute with a crystal diameter of 72 microns, or with a inlet flow rate of 1.2 milliliters per minute with a crystal diameter of 141 microns. And the fourth possibility is, for example, to use 0.48 milliliters per minute flow rate and a particle diameter of 224 micrometers. All of these combinations lead to the product being the optimum of 0.04. And the simulations show that these 4 sets of simulations collapse to yield a unique curve. This is important because this allows the scale up of information from laboratory size units to commercial units, and this concept is described further in my paper that is available online in 2024. Another point I want to stress here is that this product is 0.04. The LDF model developed by Glukov mandates that the product of the diffusion time constant and the contact time be greater than 0.1. And indeed, as I have shown extensively in my paper here and also in my YouTube presentation on failure of the LDF model, the LDF model fails for kinetic separations. This point cannot be overstressed.